Good afternoon. Hello, we are Kalman at Universitas Negeri Malang. Today, we are going to tell you about our project. Do you know that robot can see an object through nothing? So our project calls for that. And before we start, we need to know about the robot and the method first. So, first of all, let me tell you about our humanoid robot.
So, what is humanoid robots? And why are we concerned about obstacle in detecting objects? Humanoid robots modeled after humans and equipped with the ROS or Robot Operating System are utilized in various applications such as research and development, notably in software robot development. But comes to a problem where the object where we want to detect is obstructed with obstacle. For this, we can use combination of Camshift and Kalman filter for optimizing occlusion vision of an object.
Okay, so what does Camshift and Kalman resemblance of? Camshift, or continuously adaptive image shift, is a color-based tracking algorithm that adjusts its tracking window to follow an object. And then Kalman. The Kalman filter is a method that helps predict where something will be, even if it's not entirely visible. It's like having a friend that's named Kalman who's really good at guessing. For the Kalman filter's equation, we have two. The first one is the equation for measurement, and then the second one is for the covariance update. We already have surplus method, Camshift and Kalman. Then, how do we combine both of these algorithms? The hybrid Camshift Kalman filters algorithm combines Camshift for objects detection with the Kalman filter to enhance the object tracking, particularly against occlusion. But the robot cannot determine whether using Camshift or Kalman. The robot should know when the occlusion occurs and when it doesn't. So, to determine occlusion occurs, the Bhattacharya distance is used, comparing histograms of tracking features with Camshift results. If the distance exceeds a threshold, it's indicating some occlusions. Then, the tracking switches to the Kalman filter. This filter estimates the ball's position when Camshift fails by integrating Camshift for detection and Kalman error estimation. The algorithm improves objects tracking robustness against occlusion in humanoid software robots. And then we have the Bhattacharya distance. Here are the formulas.
So, we already got both algorithms and how we integrate it. So, we can conduct a program testing. In this research, two robots were used, namely Robot 1 and Robot 2. Robot 1 serves as the ball detection and tracking robot, while Robot 2 acts as an obstacle in the tracking process. The testing procedure involved extracting the region of interest, or ROI, from the ball image captured in the video and resizing it to 64 by 64 for better accuracy. The resulting color histogram showed a red color frequency of approximately 2400, forming the highest peak at around 315 in frequency, while other pins remained at 0. With the color histogram results obtained, the camera can now detect colors corresponding to the observed histogram. Based on several other tests above, combined with the average Bhattacharya coefficient values, Camshift operates optimally when the Bhattacharya coefficient value is lesser than 0.553. The Bhattacharya interval has been gotten and the coefficient cannot surpass 0.53. When surpassed, it's likely due to obstacles. When this happens, we switch to Kalman mode. With given Bhattacharya values, we can conduct observation with obstacle and integrating the Kalman filter. So, this is what we're testing. First test, we got success, where camera can shift back to Camshift while there is no obstacle. And then the second test, third test, and follows. Based on table above, tracking experiments were conducted 5 times with occlusion disturbance from the robot with an 80% success rate. In this test, the tracking was successful 4 times. After the conclusion, we will demonstrate the integrated program twice. Both of them compare the green dot where the Camshift is and white dot where the Kalman filter is. In the first test, it can be seen that the ball without obstacles can be detected easily, right? Then it is occluded by Robot 2 and still able to track the ball's location with a white dot. When Robot 2 disappears, the camera can adapt back to Camshift. Then the second test is as follows. Alright, so this demonstration illustrates that the integration between the two algorithms when detecting a ball obstructed has been implemented successfully. This concludes the presentation on the implementation of Camshift and Kalman to address obstacle issues in object detection. Thank you for your attention. Peace be upon you. This is from Humanities Universitas Negeri Malang. Wassalamualaikum warahmatullahi wabarakatuh.